Hello, in this particular lecture we're going to have a brief introductory look at collision detection, and in particular the types of collision detection that are appropriate for actually quite a lot of 2D games. It's going to be reasonably simple. Collision detection actually is a very big area, so we are somewhat only scratching the surface here. But nonetheless, that's all we need to do to get something that's actually quite useful for most of our games. A little bit of technicality here. You can make a distinction between collision detection and a collision response. So either how you detect and respond to or detect and resolve a collision. Collision detection is simply working out if two objects overlap one another. So for example, we might have two circular bounds, and if one circle goes across the boundary of the other circle, then we would say it is overlapping, it is in collision. What you do as a consequence to that then differs and can change, and that's known either as collision response or collision resolution, where you work out what do you do once you've detected a particular collision. Collisions are important for lots of different reasons. I mean, we have our games within, our objects within the games, the objects move around, and quite often we want to create a game that has the appearance of solidity, that for example, a player can stand on top of a surface and not fall through that surface. And if you think of these objects, you know, we are determining whereabouts they reside, we're determining how they move, we're drawing them out. And if we want to say that certain objects can't pass through other objects by way of giving the appearance of solidity, then there are things that we need to detect and to put in by way of response. So it's important, and most forms of games will have some degree of collision detection and collision response. When we're thinking about the game object, now we could be using a fairly complex graphic to represent the object, and there's a whole range of different techniques that we can use. In one end of the spectrum, if we have two images, so images are rectangular in size, but we may have a number of alpha 0 pixels within it to sort of etch out the shape of the entity within. Some of the more accurate forms of collision detection would do sort of pixel perfect collision detection. So there you're comparing the textile elements within each of the textures in each of the bitmaps to work out if you've got any non-zero alpha values overlapping. That's one end of the spectrum. At the other end of the spectrum, and this is what we will do and mostly is done, you can have an object. Now that object will have a visual appearance, but you also alongside this provide a bound, and that's notionally an object that encompasses or bounds the particular shape. So we'll have a couple of examples in this particular screen here. You can have different shapes for doing it. Quite often they're geometrically simple shapes, and if the if two bounds, so two of the geometrically simple shapes, if they overlap, then we assume that the two game objects themselves overlap. So common types of bounding object, you can see three of them here. Over in the right hand side we have a circle. So we can, for example, take the different objects we have and to enclose them within a circle. And obviously for the head that offers a particularly good bound, and for the arms that are stuck out, a not so good bound. But circles are one way that we can bound our different objects. And here we have, it's a person object, but we're using multiple bounds within that. The middle one is an oriented box. So if you look at for example, the head, we've surrounded that by a box. The sort of triangular torso, we've done the same there. And for the legs and the arms then that are going out, we have a tight-fitting box around those. So an oriented box is just a normal box that we can rotate and shape and size however we want to. In the middle of the screen we have axis-aligned boxes. So there we're also using box shapes, but if you look at the boxes, you'll see that all of the boxes their edges are aligned in the same direction. For example, along the X and along the Y axes. So certain ones, for example, the head and the torso, they've got the same bound. But for example, the arms now, because we can't rotate it, we have to sort of fit it within a bigger bound. So there are three different geometric shapes, and you use different ones if you want to. This is 2D. All of these things apply to 3D. You can have a bounding sphere or a bounding axis-aligned box or an oriented box in 3 dimensions as well. You can also have ellipsoids and cuboids and lozenges and lots of other sort of simple shapes by way of enclosing our objects as different types of bounds. We'll start off having a look at bounding circles as our first particular one. Bounding circles, bounding spheres in 3 dimensions, they actually offer the most simple and most straightforward bound that we can use within a game. So, as mentioned, it is the simplest type of bound. Very easy to test whether or not 2 circles overlap. It's good for objects that are somewhat circular in proportion. It is also ideal for objects that can rotate. So for objects that are allowed to rotate, if you can have a bound around the point of rotation, that's a very good outcome. So you can see here, for example, we could have a spaceship. So we could bound the whole spaceship within one circular bound. And you can see, okay, we're capturing the whole thing, but we've got a fair amount of white space. You don't have to use the full extent of it. If we wanted to, we could use a smaller bound. And there, inside the bound, we're capturing more of the ship. There's less white space, but we now have some bits that are outside of it. And you sort of got to get a balancing act depending upon the object, where you bound sufficient parts of it to be able to use to meaningfully detect collision, but without too much white space. Because if the 2 circles overlap, even if they're overlapping in the period or a section that contains white space, we'll still consider that to be a collision. And if it's too large, then it can become noticeable to the player. For bounding circles, if we want to work out whether or not 2 circles overlap, very straightforward. We're interested in a couple of distances. One distance is how far apart the 2 centres of the circles are. So it's the distance between the centre of one to distance of the distance from the centre of one to the centre of the other circle. And we can calculate that using Pythagoras' theorem in terms of the difference between the x, the difference between the y, squaring those values and then taking the square root to get the distance overall. And what we want to compare it against is the sum of the radii. So each circle will have a centre point and will have a radius. And if we add the 2 radii together, so add radius 1 with radius 2, that enables us, comparing it to the distance that the centres are apart, to work out if they're in collision. So there's no collision if the distance between the centres is greater than the sum of the 2 radii. In that case, there's a separating component. And there is a collision if the distance is less than or equal to, so the distance between the centre is less than or equal to the sum of the 2 radii. And that makes perfectly good sense. If you wanted to express this as a fragment of code, here we have a method there. We're assuming we have 2 bound object circles. We work out here the difference between their x coordinates, the difference between their y coordinates, the dis x and dis y. We're then working out the square distances. So we're multiplying the x, we're squaring the x, and we're adding onto that the square of the y. Now, if we were to take the square root of this, we would end up with the actual distance, but we're not taking the square root, because square root is an expensive operation. It's not a quick method to call. So we're happy here with the square of the distance. Underneath that, you can see we're working out the sum of the 2 radii, so c1.radius plus c2.radius. And in order to enable us to compare that with the square of the distance, we also then square the sum of the radii. And that enables us to do exactly the same comparison. So we're returning there if the squared distance is less than or equal to the squared sum of the radii. It's reasonably straightforward, very, very quick to calculate. Having looked at circles, bounding spheres, we'll now go on to look at axis-aligned boxes. Now, as mentioned, an axis-aligned box, it's one which it is aligned traditionally with the axes in your coordinate system, so with the x and the y axes. One of the characteristics of an AABB, axis-aligned bounding box, is that if you rotate the object, then you need to look at the bound, and if need be, to recalculate the bound. So a number of examples here of, for example, a cat. And the leftmost example of a cat, you can see that we have a bound displayed around it. If we go to the one to the right of that, where we have the cat slightly rotated, you can see there that we've had to change our bound. We can't rotate it. The axis line bounding box must always be aligned. It can't rotate. So in that sense, we have to change the actual shape of the bound so that we still tightly bound our particular cat. And as you rotate through, you can see that the shape of it changes. So for AABBs, they're good for bounding things which are kind of rectangular in shape, obviously, but that do not rotate. If you have something that rotates, you need to constantly, well, if it is rotating, to change the bound or to recalculate it. So in this case, AABBs, they're good for sort of platform games where you generally have objects that can fit well within rectangles that don't rotate. Whereas, for example, circles are good maybe for top-down shooters where you can have things or scrollers that rotate and move around, because then they can fit within the circle. Oriented bounding box. Now, oriented bounding box is one that is allowed to rotate, and you can see there it changes and moves around the cat quite well. So arguably, if you do have objects which are rectangular in size and which do rotate, then OBBs, oriented bounding boxes, offer you a very good fit. And that's true. There's only one small fly in this ointment, that whilst it was easy to calculate if two circles overlap, it is surprisingly more difficult to calculate if two oriented bounding boxes overlap, two OBBs. And you go from maybe having 5 or 6 lines of code to having 30 or 40 lines of code. So there's a good amount of additional complexity. By reasons of simplicity, we're simply going to look at AABBs, axis line bounding boxes, and spheres as part of this talk. You can pop along to some of the advisories if you want to have a look at OBBs. Okay, so we're looking at two AABBs, axis line bounding boxes, and trying to work out, do they overlap? This thankfully is a quick and a relatively easy thing to do, but we're going to cast it in a different way. So we're normally interested, do they overlap, true or false? But what we're going to work out is, do they not overlap? Because it is easy to think about it in terms of what conditions, if they are true, means that they definitely do not overlap. So we're almost sort of viewing this as a negated problem. We'll work out, well, what means that they're not overlapped, and do all the different tests there. And if those things are all false, it means that they must actually be overlapped. So there's 4 conditions which, if any of them are true, means that it definitely is not overlapped. And you can see them at the bottom. So if let's say A and B are the name for two AABBs. So if the bottom edge of A, if it is above the top edge of B, so where A begins at the bottom, if that is higher than where B ends at the top, then there's no way, it doesn't matter how else it is positioned, they definitely cannot overlap. Likewise, if the top edge of A is below the bottom edge of B, again, they definitely are separated. And we can do exactly the same for the left and the right hand side. So that's our 4 conditions. If any of those conditions are true, it means they're definitely separated. If alternatively all of the conditions are false, then that means, because we've covered all of the different ways that they could be separated, if all of them are false, it means then that they must be overlapping. So we can sort of view it in that way. Going back to the lecture, when we had a look at viewports, this is exactly what we were doing, where we were looking at a rectangular bound and working if that fell within the rectangular bound of the viewport itself. So in terms of the actual code that you can use here, you can have a look at the lecture on viewports. It's identical. So to finish this off, just a few other aspects that are relevant to collision detection. First one is about using grid-based approaches. So I mean, the demo we have going along this uses an object-based approach. It has a number of rectangular objects, each object kind of its own position. A lot of games, and you can see one here, Spelunky, where you would have effectively a 2D grid-based setup, and some of the grids, the grid elements contain sort of impassable, in this case sort of rock-like material. Other elements are open, you can move them through, and depending on the game you may be able to explode or to remove some of them. Grid-based setup, so here we're talking about AABBs to AABBs, so we'd have a bound for the player. Grid-based setups lend themselves very nicely to this because I can take any location or any index within my grid, and because I know the width and the height of each of the tiles that are used to display the grid, I can then convert that into an actual location within my game world by simply multiplying the tile index by the width and the height of each of the tiles. That will give me a location within the world. And I can then give that particularly calculated bound and compare it to the player's bound. And effectively, you know, if they're overlapping, then move the player back and give the appearance of solidity. The nice thing about using a grid-based setup is because if you take the player's location and you divide that location by the width and height of each of the tiles, you turn it into an index into your array. And you can then work out which tiles the player is around or close to. There may be more than one because the player will have a left, a right, a top and a bottom side. So you need to work out where each of these different, which of each of these different tiles that you're mapping onto. Another nice thing about multiple bounds, or about using simple geometric bounds, is you can have multiple bounds for an object. And over on the right hand side you can see that we have a couple of objects that don't lend themselves to being bound particularly easily within AABBs. But if we wanted to, we could simply break this down to have more than one. So we do our collision detection then not against one overall bound, but against a list of bounds. And you can define your game objects to contain a list of different bounds, and then if you're doing a collision detection, if the bound in one object overlaps with any of those bounds, then you view it to be in collision. And you can see for the spaceship examples here, we have a number of different configurations, from circular to axis aligned ones, and with different sort of combinations to give the appearance overall of interaction at different points. Just by way of concluding this, collision detection, which we've only touched upon here, and collision resolution is a very large area. We've covered enough to give some useful starting points, some useful basics to it. Ultimately, when you go down this, you're getting into the whole realms of physics and looking at response and about how things interact, and more complex forms of either collision detection or collision response. But that's beyond the scope of this particular module. So by way of one simple takeaway, for a lot of the games we can use simple geometric bounds, circles, boxes. And that will enable us to reasonably easily calculate when two of our game objects are overlap. And then we can take some action, appropriate action, if we do end up detecting that. Next talk after this, we're going to have a look at collision avoidance, about how do we actually avoid collisions. And if you have a look at the demo for this particular one, we'll look at the response. How do we appropriately respond for the particular demo to a detected collision.